There we go. So, let's continue with chapter 6. Did anyone start a homework for chapter 6? Well, yeah. Well, technically for the test, you only need the first part, just up to the part of regular induction. Did anyone start looking at chapter 8? Took a crack at some of the review problems, think you have the right solutions. Can you look at any of them? Try some of the hard ones. No, we've been praying regularly. Like I found religion yesterday. Yeah. All right, let's actually continue. We're going to do some more examples, proof by minimum concrete. So the idea here was simple, even though I'm distracted yesterday, making a lot of mistakes, but let's actually remind ourselves how to do this here and actually jump into it. So remember the idea here, it starts out as an induction proof with contradiction. To prove the PK plus 1 case. Okay. So the idea is assume there is some minimum counterexample such that Pn is false. Right? We can do this because of the well-ordering principle. We know that any set of natural numbers will have a least element, so we can always assume that if something is true for some natural number, there's a smallest natural number for which it's true, and then we show this leads to a contradiction. That's the hard part, but the idea is you want to set it up in such a way that your induction hypothesis, you can use that, and that will help you get to a contradiction. So if m in n is smallest, for which it is false, basically you're going to choose n is equal to k plus some number. So you start with k plus 1, such that you know it does not work for n, but you know it works for k, and you can use that to your advantage. Or you might have to verify several cases. You might have to do k plus 2 or k plus 3, right? You may have to do several of these things. But you kind of keep inching it toward until you find a contradiction. And at the end of the day, you are going to use the fact that it works at the number k to your advantage. And hopefully, once you distribute the plus 1 or plus 2, it'll help you to create some sort of contradictions. That's basically the idea. So let's actually do another example. A bunch of them. Where are we? Let's do this one. Very similar to the last example. Prove that 5 divides into the 5th. And this is for all integers. We're going to use minimum counterexample. Okay, let's walk through this. What do we need to show? So we have to do the base case. We'll look at P1. Now P1 says, if we look at n to the 5th minus n, that's just 1 to the 5th minus 1 equals 0, which is, of course, 5 times 0. This means that 5 divides 1 to the 5th minus 1, so you have 1 holds. And so we're assuming pk holds for some k. We show pk plus 1 holds. Right, so it starts out pretty much like a regular induction proof. The thing is, now you're going to start to change tactics. Assume to the contrary. Pk plus 1 is not. There is a minimum. They can even do pk if you want. M in n such that p of m is false.
Professor?
Yeah.
Question. I think the book does it a little differently. So one thing is like, so we can just start the proof by saying by way of contradiction, suppose that that statement is false.
Yeah. But you're assuming there's a minimum number for which is false.
Yeah, but like, would the structure matter if I put that like by way of contradiction first, and then saying that that means there exists at least one guy if that's not true, and then saying that by the well ordering principle that the guys before it must be true.
You want to just start here?
No. Because like I think in the book it's like, so proof by way of contradiction. Suppose that 5 does not divide n to the 5th minus n for all n and n.
Yeah.
Then that must mean that there exists some guide that for that is not true.
Mm-hmm.
And then by the way,
There's a minimum guide for which is true.
yeah, and then that must mean that for everybody smaller that it has to be true. Because,
Yes.
So can I say it like that?
Yeah.
Okay.
Me saying this is also saying that.
It's fine.
So if this is the minimum guy for which it's false, it means for any guy less than that it has to be true. So you are assuming that it's true up to this guy, right? This is the first guy where it breaks, right? So you look at all the possible numbers for which it is false, take the smallest one, right? Which means everyone before that it's going to work, right? So we know at least that our m has to be bigger than 1 because it works at 1. And we might need to prove some extra cases which we're going to look at. But I'm assuming there's a smallest guy for which is false, and I'm going to show that this has to be a contradiction. There is actually no smallest guy for which is false. So now what are we going to do? We're going to set m equals k plus 1. Right? Now why am I going to do that is to take advantage of what we just said. I.e., we are assuming, this implies, this has a tacit assumption that it works for any n less than or equal to k, right? Because this is the smallest guy for which it's false, which means all the way up to k it was working, but then once I went to k plus 1, now it stops working, right?
Question.
Yeah.
Okay. So I was looking up some videos on like harder questions, and then they're saying like, the question I have is like, how do you know how many base cases you need? Because
you don't. It's trial and error. I mean, there are ways, there are techniques that you can look at to kind of guess how much you might need. And sometimes the structure itself of the problem might tell you, but there's really no way to know for sure unless you're using some other number technique from number theory or something like that.
Like how would I know that that n in particular for k plus 1 would be helpful in your proof?
Well, that's what we're going to do. And I'm even going to do a problem here where we're going to have to do it like 6 times. I'm not going to do it all 6 times, but I'm going to show you what would happen to make me decide, oh, I need to do 1. Oh, I need to do 1. Oh, I need to do 1. Oh, it's okay now. So sometimes you just work, brute force it basically. And of course, in the case, in theory, something like this could go on for a long time. You can just put a computer on it. If it's something that's just iterative, just put a computer on it. Of course, if you're doing it by hand in a class, I'm not going to give you something where you have to do it like 100 times. But you're keep looking for something. You're going to look for it to break. Right? So you're going to look for something to break. So I assume this is the minimum guide, which is false. So I'm going to write it in this form. That allows me to say it's true for k and anything less. Right? And I'm going to use that to my advantage. So I'm saying the problem now is getting that +1 in here. That's going to mess things up. So let's actually look at what that would look like. So what does that mean? So here, this would be, and I can write this in blue just to show you that we're doing a little trial and error here. So what's the expression that we care about? M to the 5th minus n, right? And if you look at n to the 5th minus n, that will be, by your assumption here, k plus 1 to the 5th minus k plus 1. Right? Because that's my n. Now what would that guy equal to? Anybody remember how to expand the 5th power? It's k to the 5th plus, is it 5 k to the 4th plus 10 k cubed plus 10 k squared plus 5 k plus 1 plus k minus 1. That's it. Pascal's triangle? Yeah. It's 1, 5, 10, 10, 5, 1. Okay, so let's see where we are here. So now, ultimately, remember we want a contradiction. So we basically want to say 5 is going to divide this thing, right? Now, is it actually true that 5 would divide this thing? You can simplify a little bit here. Notice here, I can rewrite this here as k to the 5th minus k. I'm taking this guy, putting it together with this guy. Plus, these guys are left over. Let's just factor out 5. So that's 2k cubed plus 2k squared plus 2k. Okay, where do we go from here?
Well, we already know that the second one obviously divides by 5, so
Yeah.
it's an integer, but we also proved that for the expression k to the 5th minus k, that it works up to k.
This is the same as the expression here, which means I can now use the fact that, so at this point, I can say, oh, I only had to do one base case because it works out on the first step, right? Because now I can say, this is 5 times x plus 5 times k to the 4th plus 2k cubed plus 2k squared plus 2k for x, some integer x, and this happens by the hypothesis step. Right? So this whole thing is 5 times one big integer, x plus k to the 4th plus 2k cubed plus 2k squared plus 2k. And so 5 divides it. I'm missing a what?
So x plus 5 total?
X plus. Come again?
Oh, no, I'm sorry. No.
This means 5 divides n to the 5th minus n, and we have a contradiction.
Remember factoring is incorrect.
What?
Yeah, it's just k. Yeah, it's just k. It's not 2k. Yeah. This is 2k factor.
Oh, this guy? Okay. Yeah. So went through with the deduction. We verified that it works at 1, so I know my n must be at least 2 for it to work. I'm assuming it holds for pk, so I set my n to pk plus 1, so that means it works for everyone up to k, but if you go one more, that's where it stops. This is going to be the smallest guy. So then I plug that into the expression. So our assumption is that this expression is not going to be divisible by 5. Turns out when we plugged in our k plus 1, it was divisible by 5. So we end up with a contradiction. Now, it's possible to sort of answer your question a little more, that when we got here, there was no way to finagle things where I could factor out a 5. And that kind of hints to you, oh, I need another base case. Let's bring it up to 2, plug in k plus 2 here, and then maybe we can get a 5 to factor out, or then, oh, bump it up to 3. Right, so then you keep inching towards all the verifiable cases, and then so you're inching closer towards this case that supposedly exists, but you're going to realize once you get enough, it's never going to exist. Let's do another example. Prove that 12 divides this guy. So we're going to do induction on n for the base case. If I plug in 1 to the 4th minus 1 squared, that's equal to 0. That's equal to 12 minus 0, which means that 12 divides 1 to the 4th minus 1 squared. And so the base case holds. So now we're going to say assume assume to the contrary. P of n is false or something. This is the minimum integer. For which it is false. So set n equals k plus 1, and we know it would work for k. We get, so now I'm going to want to say that this guy, if I plug in m to the 4 minus m squared, which is k plus 1 to the 4th minus k plus 1 squared, you're going to want to say this is divisible by 12 and get your contradiction. But let's see if that actually happens. What's going to happen here? This is k to the 4th plus 4k cubed plus 6k squared plus 4k plus 1 minus k squared minus 2k minus 1. Now that will become what? I'm going to put these guys together because I know I can factor out a 12 from those by our assumption. Then what would I have left? I would have 4k cubed plus 6k squared plus 2k and the ones with that. right? Am I missing anyone? 5k squared. Oh, no, because this is the case where I'm going to go back.
Yeah,
So the thing is, I can factor out a 12 out of this, but am I sure I can factor out a 12 out of that? It's not clear that I can factor out a 12 out of that without me doing something else. But, so here, we have to keep going further. Were you saying something? So, what you do is verify for 2. So you can say that 12 would divide 2 to the 4th minus 2 squared. Right, 2 to the 4th is 16 minus this, that's actually 12. So P of 2 holds. So we know that m must be greater than 2, so we can set our k plus, set m equals k plus 2. And you do the same thing. So now what you're going to look at is you're going to look at k plus 2 to the 4th minus k plus 1 squared. K plus 2 squared. And I actually did this, I don't want to write out all these guys. So in k plus 2 squared, we got that, in this case, our m to the 4th minus m squared was equal to k to the 4th plus 8k cubed plus 23k squared plus 28k plus 12. That was a problem. Technically, I could have written this as 24k squared minus k. Take the minus k, put it here. I know that's divisible by 12. So 12 would be divisible into this guy, 12 would be divisible into this guy, but these two guys now are still giving me trouble, right? So there's no contradiction still. Right? So you keep going, and you keep trying to get back that old expression, k to the 4th minus k, because you know you can factor 12 out of that, and you're hoping that the leftovers you can also factor 12 out of them, so you can get your contradiction. It turns out this doesn't work here either. So basically I kept going, right? And each time I had to verify. I said, oh, and then I had to verify it's true for, I did it for 3, then I did it for 4, then I did it for 5, and I went through all these cases, and I checked, I verified these individually. But when I got to this stage, I couldn't get the contradiction. But on the 6th step, this is not fun. On the 6th step, right? So here, set m equals k plus 6. Then you look at this guy, minus m to the squared. You get k plus 6 to the 4th minus k plus 6 squared. Right, so I keep bumping up the guy that I'm using. And in this case, it ended up being k to the 4th plus 24k cubed plus 215k squared plus 852k plus 1260. Which I think would make a great test problem, personally. So I'm people crunching these numbers up. And then what I did was here, I wrote this as k to the 4th minus k squared plus 24k cubed plus 216k squared plus 852k plus 1260. I know that this guy is 12 times some integer, and so I ultimately could factor out a 12 from everyone here. So that was x plus 2k cubed plus goes into 216, I believe 18 times 18k squared plus 71k plus 105. And so now I'm like, contradiction. But yeah. So in terms of, it's hard to tell in the beginning how you would know, unless you see some kind of pattern in the expression itself that you can take advantage of, that you can factor it some way. Maybe if we looked at this as the difference of squares, something might have come to us quicker, or something like that. But other than that, you keep brute forcing it. You just remember the goal. You're saying this is the smallest guy for which it doesn't work, and then you start to see, oh, as long as you get it to work, you can stop there because that's your contradiction. But you keep going, and eventually you just verify for all points up to the stage that you're at, right? So if I verify up to the 5th stage, I'm like, okay, what about the 6th stage? I check it. Oh, now it works out. So I know that it'll work for k up to 5, for for integers up to 5, but it turns out for the 6th integer, if I assume that was where the contradiction is, it ends up not being. So there's some examples of minimum counterexample. Yeah, the ones where you have to do it up to 6 times are rare in this class. Like there's no point to me. This is me testing you on algebra. There's no point to giving you a problem like that. But I just wanted to show you the kinds of problems that might arise when using this method. And right, everything has an upside and a downside. There are times when it works in one shot, and then those times are very nice, but sometimes it doesn't. But you just have to know what you're looking for. You're looking for, when you assume it doesn't work, it actually works, and that gives you a contradiction. Let's look at another type of induction question. It's called the strong form. And this one is actually kind of similar to this in the sense that you have to verify several base cases. This is built into this method. It deals with a situation where you have to verify several base cases. So let P of n be a statement. Depending on n. If one holds 2, and technically I think they use it on if I holds for all I from 1 up to some integer k, implies if k plus 1 equals n. And that's a strong. There's an alternative way to write this if you want to think of it that way. You can say, in the first place, P of 1 holds and 2. If we assume P of 1 and P of 2 and all the way up to P of k holds, that will imply that the next guy will hold.
example in a prior class where like P of 1 held and then we started at like P of 5 for K and then P of 6 for the implication, but it didn't work for like P of 3.
Oh, that was yesterday.
Yeah.
Yeah, that was my typo. That's what I.
Oh.
Yeah, the n greater than
Oh,
5
it was 2, I think.
was a part of the question, but I forgot to write it. So we shouldn't have even been checking for 1 or 2 or 3. Like that one started with the base case of 5. But this is a different situation. This is a situation in which it kind of forces you to prove several cases before you can make that jump. And I'll give you an example of a problem where you can kind of see that it begs for this kind of treatment. So we're going to look at something, or a recurrence relation. Now, if any of you have taken differential equations, you guys have played around with this already. So it shows up in differential equations, in difference equations, and recurrence relation shows up all over the place, actually. In terms of things that are defined recursively, the Fibonacci sequence is such a thing. And you already had a homework on the Fibonacci sequence. Yeah.
Without being too extra, do we have to do P of 0?
Not necessarily. You kind of do, the problem is going to tell you where they want it. Remember, our definition of n starts at 1. Right? In our textbook, it starts at 1. There are some textbooks that start at 0 and you verify 0. If the problem wants you to verify 0, it will actually specifically say it. It will say something like, instead of saying for all n in n, it will say for all non-negative integers or something like that. It will suggest to you when 0 is something that we want to check. So here's an example. A sequence is defined recursively by the first term is 1, the second term is 4, the third term is 9, and we now know a formula to get all the other terms. an is equal to an minus 1 minus an minus 2 plus an minus 3 plus 2 to the 2n minus 3. So here's a problem. Conjecture formula for an and prove your claim. So we looked at the Fibonacci sequence before. Remember, that's a sequence that it says every new term is just a sum of the 2 previous terms, right? So that's something that shows up, and that sequence is very useful. But here's some other random sequence. We ended up in a problem where we ended up with this guy, and the recursive definition, for some reason, is a problem. We don't want to waste our computing power on that. So I want to find a nice, tight formula that can give me the nth term, right? That's the goal, right? Now, once you find such a formula, you want to prove that it will work for all n. Now, the issue is that you can see right away is that once I'm going to try to define a new term, I actually need to know the previous 3 terms, right? Proving one base case, therefore, is not going to be enough. I need to go at least 3 steps into the past, right? So if I only know the 1 step before me, that's not good enough, right? So this kind of begs to use the strong form of induction that allows us to verify several base cases to get to the next base case. And it seems for this problem, we need to do at least 3, right? I need to take at least 3 steps back to be able to make sense of this. So first, let's make a conjecture. What do you think it's going to be? Right? We know A1 is equal to 1, A2 is equal to 4, A3 is equal to 9. What about A4?
16.
Right, that's going to be, according to our formula, n minus 1, that's going to be A3 minus A2 plus A1 plus 2 times So that would give us 9 minus 4 plus 1. This is 8 minus 3, that's 5, so that's 10. So that is actually 16. So here's our conjecture, which is a fancy way of saying guess. What would you guess that an is equal to at this point?
N squared.
It seems like the n squared one, right? So at a1, that's 1 squared. This is 2 squared. This is 3 squared. This happens to be 4 squared. That seems to be, right? So if I somehow I'm working on some problem and this recurrence relation shows up, I realize, hey, this is just the n squared function. Because that's 1 squared, that's 2 squared, that's 3 squared. And this guy here is 4 squared. So that seems to be a natural conjecture. But remember, we never make some general claim based on a finite number of examples. It could break at some point. Who knows? Look at this random formula here, right? How do I know that's always going to give me a perfect square, right? That's something we have to prove. It works for the first 4 terms at least, I can see that. But how do I know it's going to work for the 9 billionth term? Right? Induction. Right? We want to show it's going to work for any n in n. And we want to use that induction. But the problem was I need 3 things in the past, so I'm going to use the strong form of induction. Let's verify several base cases. Well, let's actually make a claim first. The recursive sequence. In terms of the recursive sequence, is given by an equals n squared for all n in n. Proof. We apply the strong form of induction. We have verified 1, 2, 3, and 4. That should be enough. Let's actually get into proving this and see if we might need more. But we know that we've proven the first 4. So we know P of 1 and P of 2 and P of 3 and P of 4 holds. Assume I'm going to assume it holds for everyone up to k. And we're going to show pk plus 1 holds. So what do you think of doing here? I need to verify. So we assume that a to the k equals k squared. This means that a to the k plus 1 would be equal to all I, where I plus 1 to k, well, for all k. How do we get a to the k plus 1? Huh? What? Huh?
Say k plus 1 squared.
So it'd be k plus 1 squared?
Rewrite it using the recursive definition.
Right. Why would that not be the thing to do?
Begging.
It's begging the question. You need to prove that it's true for the k plus 1 term. Right?
No. Using the recursive definition like that. Is that still wrong?
He's agreeing.
Are you agreeing with this statement? Because you have to prove it. You do realize this is the statement pk plus 1, right?
But to show that we get that.
You can't just write that down. That's begging the question. You're assuming what you have to prove. I can't just say ak plus 1 is immediately this.
I think by using the recursive formula, he means literally plugging into an equals an minus 1.
Yeah, we use this, right? I can't just jump here, right?
No, can I say that, I'm saying that based on my conjecture, that I'm supposing that's true. And
Yeah,
then,
which means you're supposing this. We're supposing it's true up to k, which means at the k plus 1 term, I don't know if it's true or not.
no, I know, but I'm just saying that just based on like with algebra, that I'm representing k plus 1 as some trinomial or whatever.
Right, so we have to use this. Right, this is how the sequence was defined. So this is what we know is true. Right? So what I'm going to do is I'm going to plug into here, right? Where my n's are now replaced by k plus 1. So this is going to be a k minus a k minus 1 plus a k minus 2 plus 2 times 2k plus 1 minus 3. Right? Now I can say that because that's how the thing is defined. That's what we verified is true, or we were told is true. Right? So I can say that, but I don't know that this is a perfect square.
No, what I'm saying is that like the way I did it was like, I'm just trying to say left-hand side is equal to right-hand side, and I'm saying that I'm just looking at whatever k plus 1 for k is an integer. And then I'm saying that that thing is equal to some trinomial, and then that thing is equal to the same guy, and then I'm trying to link them together.
I don't know. I'll have to see how you wrote it down, because I don't think. Right, you can't say this is equal to a perfect square in the beginning. That's totally wrong. Okay? So this is that based on that formula. So we need to prove that this is the perfect square. Well, what is AK? That's k squared. What is AK minus 1?
K minus 1 squared.
K minus 1 squared. Now why could I say that, but I couldn't say k plus 1 squared?
You've already proved it for all elements up to k.
Because I'm assuming that it will hold for all guys up to k. So it's going to hold for k, k minus 1, k minus 2, k minus 3, all the way down to 1. The thing is, I don't know if it holds for k plus 1, k plus 2, k blah, 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 right? I need to prove the future, right? But I'm assuming everyone in the past it will work. So everyone where their subscript is k or less, I can assume it's going to be a perfect square of the subscript. For k plus 1, I cannot assume that. That needs to be proven. So it'll work here, it'll work here, it'll work here, because those guys are all less than k. And this is going to be 2k, this will be plus 2k minus 1. Right? And now I want to show that this actually simplifies to what I'm hoping it simplifies. In order to verify the induction, I need to prove that ak plus 1 is equal to k plus 1 all squared. So this is k squared, this is minus k squared plus 2k minus 1 plus k squared minus 4k plus 4. This is going to be plus 4k minus 2. Is that fine? So this kills that. I have a k squared here, so that's that. I have 2k minus 4k, that's minus 2k, plus 4k, that's 2k. I have minus 1, minus 2, that's minus 3, plus 4. So pk plus 1 holds. Now that's a common mistake, which is why I keep beating this dead horse. That's a common mistake for students to make. You have to be very careful not to beg the question. You cannot say this equals to this at the start. You are wrong. No matter what you say after that, it's wrong.
No, that's not what I'm saying. I was just saying.
I'm not sure what I don't think I get what your sentence was. Like at this point, what did you write down?
So I didn't even. So the goal is to show that k plus 1 squared is the k plus 1 term is equal to.
The goal is to show that ak plus 1 equals k plus 1 squared. That's the goal. So what did you write
So
down?
then I said that k plus 1 squared is equivalent to k squared plus 2k plus 1.
Sure.
So that's the same. So I'm trying to prove that. So then on like the side or on the right hand side, I'm basically doing that.
So you did this,
Yeah.
and then you simplified to get to this, which is here.
Yeah. So I think that it was just because I was doing the work, and then I looked up and I didn't see what.
That's fine. So you can say, I need to show this, and then you start, and then you can start this, which you know is this, and then you get it to this point. That would be fine. Yeah. The important thing is you have to make sure that you never actually assume this is the case. You have to actually prove that. You have to build up from it. So you can't just write that down. You can't write down this equals that. Any other questions on this?
What happens if we can't get if we can't come up with a simpler formula just by using different values? It's like let's say we can't make conjecture underneath, or it's not so.
Oh, well, you'd be stuck at this point in the problem.
Yeah.
Is that what you're saying? Well, that's a different problem altogether. That's not an induction thing. Usually, and it is true that in general, coming up with a formula for a sequence is insanely difficult. Right? It's not something that happens in nature very often. But if I'm going to ask you a question in a test to conjecture something, it would be something that I would expect you to be able to look and kind of figure out. So here it was kind of obvious, and with most of the questions, it's going to be that way. But yeah, to be able to say this in practice is not an easy thing, and that's fine. So another example. So yeah, conjectures in general are not easy. But yeah, assuming you could get to the stage, which in a class like this, I'm not going to make it seem difficult to get to that stage. You should be able to prove it from that point. And the question kind of hints to you that you will need several base cases because it needs 3 previous terms. So that kind of hints to you the kind of induction you want to use. Here's another example. Proof for every integer. Not going to create this time, greater than 12. Right? So it doesn't always apply. n will be 3a plus 7b. In other words, every integer 12 or bigger, you can write it as a multiple of 3 plus a multiple of 7. So, for the base case, what is p of 12 would say?
8, 4,
So 12 would be equal to what?
equals 4. Or 3 times 4 plus 7 times 8.
Is 3 times 4 plus 7 times 0. And that works. So it's a multiple of 3 plus a multiple of 7. So I don't want to start this using strong form of induction, but let's actually just kind of run with this so you can see where strong form might be needed. Because it's not immediately obvious here at this point that a strong form is required. So let's continue. Assume pk holds. We show p of k plus 1. i.e., assume that any integer k, I can write it as 3 times a plus 7 times b. And we need to show that k plus 1 can be equals to, this is I and j. And k plus 1 can be written as 3 times a plus 7 times b, or ab. Okay. How would you go about that? So one thing might jump to mind. You might want to do something like, okay, what if I take this and add 1 to both sides? You realize that, okay, I have this random plus 1 out there. How am I going to absorb it into one of these notes?
For every 2a, you can just throw the line and make it b, so to speak. So to speak, you can, for every 2a, theoretically just shove the 1 in there and make it a b. Kind of, like if you were going to go
for every 2a?
Yeah, like if you were going to go from 12 to 13,
Okay.
instead it would be like 3 times 2 plus 7 times 1. The 2 3s would be a 6, so you just move the 1 into there, make it 7.
Okay, so okay, so, but how would you do it here, given this information?
B equals 2i plus 1, or no.
I remember there was some similar problem in a previous section where you could do it by the thing, but I think it uses a division algorithm, and then you can write.
Yeah, well, we're not using it. Let's go further. 13, does it work for 13?
Yeah, 2 and 1.
So, you have 13 holes. 14?
0, 2.
have P of 12 and P of 13 and P of 14. So, by the way, why do you think I only verified 3 cases?
Is it the division thing? Is that what you're talking about?
Almost, but it's something based on this problem. Why would I go 3? Why didn't I go 4?
Because after you get 3, you can just write it as.
The idea is I want to get 3 guys over here that when I can move over, I can factor into here, right? So I could have gone for like 7, but why go for 7 when I could go for 3, right? If I get 4 extra things to play with, then if I move it over, I can't really factor. So I'm like, okay, I want to be able to bring things on the other side to solve for k, and I can factor them into this nice form. So I'm going to think, which guy would I rather things be absorbed into? The 3, because it's the smaller numbers. So I'm hoping, okay, let's prove for the first 3 things, so I have some leeway here. So we can assume that k is at least 14. Which means that k plus 1 is at least 50. And so I can do as much as subtract 3 guys from this guy to move them to the other side. That's ultimately what I want to be able to do. If I take k plus 1 and I think of it minus 3, that is at least 12. And the claim would hold for this expression. Since if I take k plus 1 and minus 3, it's actually going to be less than k. Assuming it holds for up to k, it will hold for this expression. This expression will allow me to subtract 3. Then, turns out that k plus 1 minus 3, I would be able to write as 3a plus 7b. This is less than k, so the claim holds. So I can write this for some a, b in the positive integers, non-negative integers, which means that I can write k plus 1 as 3a plus 3 plus 7b, or 3a plus 1 plus 7b. This guy is non-negative since a is non-negative. So I want to be able to move a 3 to the other side so I can factor it out. And so what that forced me to do, let's verify 3 cases. So I realize I can subtract off 3 and move it to the other side and still be okay. Right? Because I'm always going to be, within the range that I care about, and this expression will be less than k, it will satisfy everything, and that allows me to move this 3 over and factor it out. So it turns out that this is true. Every integer bigger than 12 can be written in this form. It's a multiple of 3 plus a multiple of 7. So that was a weird one, I admit, but the homework will practice a few more. typically, if I'm going to ask something about strong form induction, which is not going to be on this test, but probably in the future, it'll be on usually like the recursive form, that kind of thing. Because those show up all the time, so it's important to know how to do it. Okay, that's the last thing I wanted to do in this section. So I'm kind of bored with induction, so let's finally. Chapter 7. Again, we're not going to learn anything new here. This is called prove or disprove. The goal here. So I'm going to throw out some statements to you. We're going to try to figure out together whether or not they're true, and then we have to prove our assertion. Again, not on the test tomorrow, but it's something that we will be doing in the future and something that you will be doing in the future. If you're going to be doing mathematics, right? So sometimes you want to be able to prove something and you want to know you're not going to be wasting years of your life trying to prove something that's not true. So you have to have a good reason to think it's true in the first place. Or sometimes there's something that you want to prove is true, where you have very strong evidence to prove it's true, but on your way to proving that's true, you end up with a roadblock where you have to prove something else is true, and then you have to make a guess at that point. Right? So things like that will happen all the time. So sometimes you're given a statement, you want to make an educated guess as to whether it's true or not, and then figure out a way to prove your claim. So we're just going to do a bunch of examples here, and we're going to try to figure them out together. For all n, so here's the claim. So this is the main goal. Given the claim, determine if it is true or false, and justify. Of course, justify by proof where necessary. So here, for all non-negative integers that start from 0 and are positive, there exists another non-negative integer such that please. Start with the first one. True or false? What do you think? True? Prove your claim.
Is it false?
False by counterexample.
What's your counterexample?
0. Can you also make the argument just that because it's a set of integers, it's a or in general, just because it's a set of integers, there must be a least element?
Yeah, it's a non-negative set of integers, so it must have a least element. You can prove, in fact, it's kind of an extension of the well-ordered principle, but you can sort of prove that, yeah, any set of integers that has, from some point onwards, will have a least element, based on the well-ordered principle. But yeah, that's a counterexample. There is no k such that k is less than n, and at the same time, k is also itself non-negative. So once you see this less than here, you're going to think about and so things like least elements. Right, so you start to think about things like least element being less than, is something always going to be less than this? And then you're thinking, oh, but I'm stopping at some point, so that means it kind of hints to you that there is some least element, so there must be some guide that's always less than or equal to things. But when you force it to stop somewhere, the guides that can be strictly less than will exit that set. So that's actually false. I think it's true. How do you prove that? Yeah.
Question, are we assuming that the negatives are involved as well?
Yeah, like there's no, I didn't restrict you to positives or negatives.
That's true.
Okay, see it's true? True.
Okay.
Let a equal to 1 plus 1 and b equal to k plus 1.
And B,
Is equal to k plus 1.
okay,
Equal to a plus b. So when it's plus when plus k plus 1 is
okay. So, is that a proof of the claim?
The counter.
Hmm?
No, I just need to find at least, actually, no, it doesn't matter. I can start by saying, so let an even integer be given.
Well, no, I want to address the question I just asked. Is this a proof of the claim?
Proof of the counter. Or not the counter.
So I'm going to say this is true, and they wrote this as a proof. Did I prove the statement? What is this saying?
Some of the like
Right, this is proving the statement that if I add two odd integers, I will get something that's even. But that's not the statement. The statement starts out with me giving you an even integer. I give you an even integer, show me you can write it as the sum of two odd integers. It's different from saying I had two odd integers in the first place, and when I add them, I got something even. So this is actually not justification of the claim. It is true, but this wouldn't be the proof of it. This is proving something entirely different.
Can you let a equal 2k? Starting with some even
Okay,
integer
so given, I don't know, let's read this in blue because we're not sure. Given a in Z, you're assuming a is even, okay? We can write with a equals 2k.
And then set that equal to 2L plus 2.
Why would you be able to say that?
Because
You want to set,
if L
you
is
set this equal to,
2L plus 2,
and how does that apply? What did you just do?
I took out one of the 2's in K, where L would be K minus 1.
Or L equals k minus 1? Okay, sure. And every integer is, you can think of it as one guy away from another integer, sure.
And then you could say that that's equal to split L even further and make it, 2J plus 1 plus 2R plus 1.
So, and then you're splitting this again?
Yeah.
Okay, so this is 2. So you're going to say r plus,
Plus 1. Parentheses. Yeah, plus.
you're just writing L as something plus 1.
Oh, no, sorry. So
Can we split 2k into k plus k? And then consider the cases? And then I
K
show,
plus k.
yeah, and then I'm actually going to prove that, but prove something stronger. Saying that for any two, whether k can either be even or k can either be odd. So even plus even is even, and odd plus odd is odd.
Okay.
And I don't care about the first case, case 2, just yes.
So you want to write, okay, 2k is k plus k, and you basically want to argue that I can always choose k to be odd.
And then I'm just like considering the possibilities for k. And then I'm saying that k can either be even, but then I have an even plus itself, it's the same guy, so that's even. And then I can say the other case would be the odd, because odd is the thing that you want. Would that be fine?
Okay. Oh, so okay. So I see what you're saying. You could say that. So basically, you can say we prove a stronger claim. That for all n in Z, if n is even, then n is the sum of 2 even integers, and it's the sum of 2 odd integers. Is that what you're trying to say? So if this is true, then the first claim is true? Is that what you wanted to say? Like say if we have this, we can split it into k plus k, and I can choose k to be even or odd, and it will still work.
I don't write it like that.
Are you allowed to make a choice
No, I
on
didn't write it like
k?
that, bro.
what I was trying to.
I think what he's trying to say is that k can either be even or odd. It
Okay.
can't be anything else. So you take one case in which k is odd, and in that case you're going to get the sum of 2 odds that are the same numbers. So you're going to get 2k, which is even. Or you can have 2 even numbers, in which case 2 even numbers summed together is going to be an even number of terms.
Okay. Yeah, I thought that's what you were saying. In fact, we proved that already in the class, but how do you know I can choose to make them odd? Because I'm saying it has to be odd. And they have the sum to a given a. They have to sum to that particular number.
For what I was trying to do, where I had like plus 2, I was saying, oh, aha, I made it plus 1, but then would I have to have the original k be divisible by 4, just splitting even further to make it like 2 something plus 1?
The important is you want to make sure that the a itself is going to be the sum of the expressions, whatever expressions you conjure up. Like how do you know, okay, I can choose, this will work whether k is even or odd, but how do I know I can choose odd numbers so that these two k's will add up to that particular k?
Because a is an integer.
It's an even integer. Yeah?
We assume that k is odd.
Yeah, how do you, okay, so assuming k is odd, it'll definitely add up to some even integer. How do I know it adds up to that one? I can just say, oh, here's an expression k plus k. I can choose it both to be odd to get an even integer. Can I do that to get any particular even integer that you hand to me? Can I choose a k such that that would work?
Kevin, but is this an existence proof? Do I have to show, do I have to construct the thing for you? I can just show, it's like that cheat trick, your rationality. I'm saying that it exists.
No, well, no, this is a lot stronger. It's saying every even integer can be expressed this way. There's a way you can say that I can always choose the k to be odd such that this will work out.
Wait, is
That actually, that's a super strong claim though. You'll actually need something like the axiom of choice to make that claim. You're going to invoke some really high level math in order to say that. I can actually give you something easier for the sake of us moving on.
But wait, we're so close.
Can we try proof?
Try to construct it like he was. There's a construction. And we can use the ideas that we've expressed before as, you know, the sum of two, an even is even, the sum of an odd and an odd is even, sum of an even and an odd is odd.
Are we allowed to use proof by contradiction? Since it says F, we can try to say there exists one even integer for the sum of two odd numbers that is not equal.
Okay, and how did you get the contradiction?
Because when you add them, you would end up with an even.
Yeah, but how do you know it's not some other even?
Proof by cases.
Would you just say for every single value of k? Choose some k that is
You're tapping out. Yes, yes, that's what I wanted. Gave up on the second example.
Is it possible to prove by cases? Sum of two odd, sum of two odd, and some odd and even?
No,
It doesn't really work, right? Doesn't make
it
sense.
doesn't work. Because you're starting from the other end. That's why that's a problem. I need to start with an even integer. Here, 24. Can you write that as the sum of two odd integers? Right? So the fact that you can say 24 equals k plus k, can I choose that to be two of the same things? Would I always be able to say that? In fact, can I choose two odd integers that have the same value that will add up to 24? You actually can't,
Okay, how about this?
right? So that kind of thing is not gonna, that kind of construction won't work. So you guys are thinking from the other end. You're thinking of, okay, if I'm given two odds and I add them, I'll get something even. Yeah, how do you know you'll get that particular even? Give me two odd guys that will work here. It can't have this form, right? So you can't assume this is true. Because I gave you an example where that's not the case.
Can we say that for any even integer? 1/2 of that integer plus 1 added to 1/2 that integer minus 1.
Okay.
You're super close.
Wait.
He's close.
Can you rewrite it as 2k minus 2 plus 2?
No.
2k is equal to 2k minus 2 plus 2.
Okay, so both of you are now close to something that can work. So by your powers combined, like what is
So we have an even integer 2k.
Rewrite that as minus 2 plus, or 2k minus 2 plus 2. Then I factor out a 2 for each guy.
Yeah, you're going too complicated. Do what you're trying to do with A itself. Then A is equal to
1/2 a plus 1 plus 1/2 a minus 1.
Yeah, that can also be if it's odd.
You can say the half because it's even, sure.
But you can't necessarily justify that that would be odd or even since, unless it's originally divisible by 4, you wouldn't have a.
Can we just say
So again, it's too complicated.
Yeah.
But what did you say? 1/2 A plus 1?
Plus 1/2 a minus 1.
and it's both odd?
Sure. What can you tell me about this guy?
Must be odd.
Has to be odd. That's an even number plus an odd number. What about 1? That's also odd. Yeah, okay. Moving on. That's just me having a little fun wasting time. Okay, so is that true? If the intersection of two sets is empty for every set B. So A is a given set, right? So there's no restriction on A. Here's the set A. I can give you a set. It could be the empty set, it could not be the empty set. Here's a set A. If I take the intersection of that set with any other set, it's empty. Does it mean that the A has to be empty?
No.
Yes.
No.
Yes.
Let B equal
Maybe
A.
not.
Choose 2 finite sets that are unique with distinct elements.
Yeah.
So you say this is true? Okay. So
Let A equal B.
let A be a given set. Then what do you want to say?
If B equals A, then the intersection equals A.
If you choose B equals A, then A intersect B equals A. That's true. What do you want to say with that?
Therefore, if A intersects B equals A, then A intersects B. And A intersect B equals the empty set, then A equals the empty set.
Wait.
Oh, that's one example.
Yeah, you're choosing if someone happens to choose the same set B as A. But yeah, that kind of hints to you that what you're saying is correct. So I think what you're saying will work nice maybe in a proof by contradiction. And assume A is not empty. Yet A intersect B is empty. Right? So I'm assuming that this is true, but that is not true. Let's get a contradiction. Since A intersect B is empty for any set B, this must be true for B equals A. But then we have A intersect B is equal to A, and which is non-empty
But it's also
by assumption. Contradiction, right? Because we assumed it was empty, and then I get the fact that it's not empty. Contradiction. What about this one? For every set A that is non-empty, there exists a set B such that the union is empty. No matter what set I give you, can I take the union of that set with, does there exist a set out there? I'm not saying for every set. Is there some guy wandering around out there that if I take its union I get something that's empty?
Can we also do contradiction? Since A must be a subset of A union B?
We know A must be a subset of A union B. Right, by the way, I don't remember if we pointed that out before, but that's actually a nice thing to know. But some of your homework problems suggested it to you, but I'm not sure if I don't remember if I specifically said it. But something like that is a nice thing. A union B is a very big set, right? Each individual set would be a subset of it, and the intersection of each individual set is also a subset of it. So it's a very nice thing to be aware of. Okay? So if we know that, what can I say here? Notice that if I assume this guy was empty, right, and my A is not empty, then it kind of tells me that there's some non-empty subset of the empty set. So that kind of doesn't make any sense. So here, I would say this is false. If A is not empty, then A union B. But let's write it down a little nice. A is not empty, then there exists some X that's in A. But if X is in A, then that means X must be in A union any other set, right? Because the union is just contains any elements that are in A or some other set. I know something's in A, therefore it must be in its union. In fact, that's me making this claim, right? A is a subset of its union. But that would imply that A union B is not empty, because there's an X in it.
Wait, that's one question. That other question, that's true?
This is true, yes. This statement
Is that the one, is that the same as saying for all A, for all B, A implies B, the empty set implies that A is not equal to B, the empty set?
Yes.
What about if I have, like two finite sets? A is equal to 1, 3, and the other one is equal to 2, 4.
So A is equal to 1, 3, and
B is equal to 2, 4.
2, 4. Yeah.
And then their intersection will be empty, and A
Yeah.
is not empty.
A is not empty.
A is not empty. A is not the empty set.
Oh, your problem is you're choosing to be.
Well, isn't that the same as for all A, for all B sets? Like that? Like your statement, right? That's like, can I move that for every set B to, like, as a second sentence? Like, let A be a set. Isn't that saying, like, for all A?
For A is any set, yeah.
So for all A, for all B,
A is a given set, and I know, if we assume that its intersection with another set is empty, no matter what that set is, then this set must be empty.
so, but then that's an example where that's false.
What if B is the empty set? No, you need to prove that for every single
No,
one.
the thing is, you need to show for every set B. You just show me, here's a particular one.
It's like the example with the,
Like, for example, I could say that is some other random set. The intersection is not empty. Or that B, I can choose B to be A, I can choose B to be anything. I can choose it to be anything at all. And the claim is, no matter what you choose it to be, the intersection must be empty. But there are choices for B where the intersection is not empty. So there are choices of B where the first part is not going to be fulfilled. Right? For those choices of B, I have an implication where the first statement is false. So it's true vacuously. Whereas for the other choices of B, it's A has to be empty in those cases. Maybe one more for the road. Let's do the opposite. What about the union? This same statement here, but with a union instead. set if this is not empty. For every set B, then A is not empty. And here's some more you guys can think about for later. Remember, this is our notation for the power set, right? So I'm just asking, is the power set of the union the same as the union of the power sets? If A minus B is equal to B minus A, then A minus B must be the empty set. True or false? Is that true or false? There's just a couple more examples. I'll just write them down. You guys can think about them over the weekend. Maybe we can even do the homework for the chapter. Because why not?
Because we have chapter 6. 6 and
So
7.
if A is a subset of C, B is a subset of D, and A intersect B is the empty set, then C intersect D is empty as well. Again, I'm not saying this is true, you have to tell me if it's true or false. And finally, for all positive integers, this guy here is prime. Very interesting claim to make. What about this one? Is that true? If the union is not empty, no matter what set I pick, then A must not be empty.
You can let B be the empty set.
So you're true or false?
False.
You think it's false? Okay.
Oh, sorry.
So you're saying if A is the empty set?
I'm going to say true. If B is the empty set, then the union. Yeah, if B is the empty set, and the union can't be the empty set, then there's just an element X in A union B that isn't in B, since B would be the empty set. So
Okay.
therefore, X must be in A.
Okay, so you're saying it's true?
Yeah.
But you picked a particular set. So how would you prove it? So you're claiming it's true. It's an implication. How are you going to prove it? You want to do it directly? So you're saying if A union B is not the empty set, for all B, then in particular, this holds for B equals the empty set.
Yes.
Since there exists an X that's in A union B, and we know that X is not in B, because B is the empty set, we must have X in A. that argument work? This holds for all B, must hold for the empty set as well, if that assumption is true. And so that's the case.
Well, for any other set B, wouldn't, if B is not the empty set, I guess we could prove by cases B is the empty set, B is not the empty set, and if there is an element in B, then there would be elements in A and B.
Okay. So if B was not the empty set, then this is true. That would mean X is in A or B.
Oh, then A could be the empty set.
That's false.
It's actually true. But you can see this proof is kind of something that someone can argue with. So I probably wouldn't want to do that. What about by the contrapositive?
Well, assume A is the empty set.
How would that be?
Assume A is the empty set.
Assume A is the empty set.
Then there exists A set B.
But, so let's actually do a contradiction. That would probably be nice. But A union B is not empty for all B.
Then take B equals the empty set.
Then it must hold for B equals the empty set. But then A union B would be empty, and that's a contradiction. Alright, so that would cover all the grounds. Okay, now, well, what about this? What about that? Well, I assume this is true. I assume this thing is false, and then it actually didn't work. As opposed to you writing a proof where you picked a particular guy that's going to suggest what you want to suggest. It's valid, but you kind of have to be a couple more minutes for that. So we'll stop there. Remember the test is tomorrow. I'll post the solutions to the review in a couple minutes. So hopefully you were trying them. So again, you need a lot of practice on these. That's the only way around it. So make sure you know the definitions, make sure you know the proof techniques, how they work, how to organize a proof. But you should really practice on this, applying to a variety of different cases. That's it. Good luck tomorrow.
I don't know if you want to say,
You know,